Hi, everyone. My name is Victoria with 82mag.com, and I'd like to thank you all so much for joining us today. The topic of our webcast is PostgreSQL with built-in resilience and on-demand scale. Is this a dream? Sponsored by YugabyteDB. Before we begin, just want to cover a few housekeeping details. We will be having a Q&A session at the end of today's event, so if you have any questions throughout the presentation, please make sure to type them into the Q&A box. YugabyteDB has also provided some resources which do correspond with today's event, so take a moment to check those out. They're going to be located to the right-hand side of your audience console. Today's webcast is also being recorded, so make sure you keep an eye out for a link in your email to rewatch the presentation or to share it with a colleague. And now I'd like to introduce you to our speaker. Today we have the pleasure of hearing from Karthik Ranganathan, founder and CTO of YugabyteDB. So we're in for a really great event today, and with that, I will pass the time over to Karthik to get us started.
All right, thank you. Thanks a lot, Victoria. And hi, folks. Thank you all for being here. I'm Karthik, as Victoria said, one of the co-founders and the CTO at Yugabyte. And here we are. At Yugabyte, we're big believers in Postgres, and here we're trying to make Postgres better. We're trying to make relational databases better for cloud-native applications, and specifically, we've done these couple of things, built-in resilience, on-demand scale, and a few others. So let's dive right in. Quite a technical presentation, but feel free to drop questions if you guys have any, and I'll try to address them as relevant. All right. So as I was saying, we really love Postgres, and we are trying to make Postgres better and make its adoption grow even more and make it more viable for cloud-native applications. So why Postgres? Well, Postgres has indeed become the default database API. Everyone's adopting Postgres, so it's no secret. And there's a lot of core ingredients that go into it, like its maturity and the fact that it's a proven database, very easy to use. Developers love it. It's extensible. It's got a huge ecosystem, huge community behind it. It's, in fact, the fastest growing database in terms of adoption and popularity. So all goodness, right? Now, let's say if I were to pose the question, what does your dream Postgres look like? Well, we did just that. We asked a lot of people, what does their dream Postgres look like? And asked us to give a to-do list. What are the things you need in Postgres, right? And here's what we got back. Well, the first thing was, don't compromise on Postgres. It's got to be exactly the same Postgres, whatever it is you do. And on top of that, connection management, was generally a pain point, and people didn't want to deal with that. It would be great if that would go away. And make active deployments easier, which means give high availability in a region, multi-zone, multi-AZ, multi-region type deployments. Make it much easier. Make it easy to migrate from other databases. Specifically, Oracle comes up a lot, DB2 comes up a lot, SQL Server sometimes, and so on and so forth. And then scale when you need to, and just when you need to, and very quickly. And lastly, with cloud architectures, data is all over the place globally. So make it easier to build these global architectures, right? So these are some of the things we're going to take a look at. We're going to take a look at each of these and go into what has YugabyteDB done. YugabyteDB is an open source database. It's based completely on Postgres. It reuses the upper half of Postgres to a point where you can barely tell the difference between YugabyteDB and Postgres. So our aim is to make it easier for you to stay on Postgres while being able to address a number of these things. So let's dive right in. Okay, so the first thing was it's got to be fully compatible with Postgres, right? Now, it's important to recognize that, a lot of databases are starting to become Postgres compatible, but it's important to understand what is Postgres compatibility. There's many levels of compatibility. There are databases which work with the Postgres client drivers and understand the syntax, but the way they implement those features is very different, or sometimes they just skip certain parts of the syntax and don't do whatever it is you want, right? And then there's feature compatibility where they'll give you equivalent features to what Postgres has, but they work differently, and you have to relearn and or change your application to work accordingly. And the highest level of compatibility is just make it look like Postgres. You can take a Postgres application and run it against this database, and it should just work. At YugabyteDB, we opted for the fourth, obviously, but it's just something for everyone to be aware of, that there's different levels of compatibility, right? And full compatibility is super important. And the only way we were able to achieve it, and it's probably fair to say anyone can achieve full compatibility, is to reuse the code, right? And that's why you see a lot more Postgres compatible databases and a lot less highly compatible Oracle or SQL Server. It's just hard to emulate a database when you don't have its code. Now, Postgres is fully open source, which made for a great starting point for us. So the way we do this is we completely reuse the Postgres query engine, and we have a highly replicated and transactional storage layer, which is cloud native. Right? So everything that your code used to talk to in Postgres is still the same thing your code talks to, the same old Postgres, but the way Postgres actually executes the queries has changed to go to distributed execution. So let's look at this in a little more detail. Right? In this diagram on the left, you have Postgres, the query engine, talking to Postgres' storage layer. On the right, you have the same Postgres query engine, which is now modified to talk to a distributed storage layer across different nodes. Right? And that's what YugabyteDB does. It takes the query engine of Postgres and makes it distributed ready. And on top of that, it really understands everything in Postgres, the system catalog, the various different types of, let's say, data types, query types, various different features such as stored procedures or triggers, or, say things like row level security or permissions, all of that remains the same. So the best way to prove this is, actually take some real world complex applications and try to run it, the applications that run on Postgres, and try to run it on YugabyteDB. Right? And that's what we did here. Here are some very popular applications. You might have heard of some of these. So things like Mastodon or Redmine or a whole bunch of others like GitLab, Jira, very, very popular applications. We were able to simply get it to run on top of YugabyteDB with no changes, right? And a lot of these applications are actually non-trivial. When you look at under the hood how an application is built, over time, as an application evolves, it uses more and more of the underlying features that databases like Postgres give them. Right? So in the case of Mastodon, there's 422 different types of objects spanning across tables and indexes and functions and sequences and views and a whole bunch of others, right? So all of this simply works on top of YugabyteDB because it's the same code, right? And in fact, we've had the example of one real-world application. It's not an open source application, so not putting its name here, but it is a core banking application that had 67,000 different types of objects, right? And it simply was able to move over to YugabyteDB. And the reason for this is because everything is the same as Postgres down to the system catalog. Okay, so now, what you're thinking is, great, the code runs, everything works, but what about the performance, right? YugabyteDB is a distributed SQL database. And the question is, can you simply move your applications, or do you need to re-architect them for the distributed world? And we started out as a pure distributed execution database. But here's where what we've announced recently. We've added the ability for queries and operations to run exactly like it runs in Postgres if the data is local. So you can start out with local execution and then move over to distributed execution. Right? So what are some of the things we do? Just to explain, when you have distributed execution, as this diagram shows, the first thing that you think about is how many times do you fetch data over the network? Fetching data from local disk is really quick, but fetching data from a remote location takes a while. So if Postgres fetches, say, 100 rows and is fetching it from the local disk, it's going to be a few microseconds per fetch. It's going to be a few milliseconds for the 100 rows. It's totally fine. When you go distributed, those microseconds become milliseconds, and so your query now becomes hundreds of milliseconds, and that's really the challenge that you run into. So some of the things that we've done is make the query execution work exactly like Postgres when it is local, but transparently switch to distributed remote execution. And enhance the cost-based optimizer for multi-node and geo-distributed deployments where you have to worry about the network cost. And also think about transparently rewriting the query so that it's more efficient in the way it gets executed. Okay, so before I go further, there's a bunch of questions, so let me answer some of these questions. The first question is from Lynn James, which is, why is built-in resilience important in the context of database management, and how does it benefit organizations? So it's a very fundamental question. Thanks for asking that, Lynn. If you think about it, every critical application needs to be always running. Users today have the expectation that you don't have downtime in services. How do you ensure that? Well, if an application instance, a node which is running the application software, the code goes down, you can bring up another node very quickly to take its place. Because after all, the application doesn't have too much of state or storage. But when a node running the database, like Postgres, goes down, what do you do? Well, in this case, you have to have a replica. You have to promote the replica. But when you have a replica, which is asynchronously replicated, your problem is you lose data. So how do you write your application to now recognize this loss of data? And when the node goes down, somebody has to come in and promote this replica to become the new primary and serve it. And the problem also is in the cloud, you have far more failures like VM failures, disk failures, node failures, zone failures happen very, very often. In fact, in one of the surveys that we did, we saw that there was a major outage. I'm not talking nodes or VMs. I'm talking major outage once every 50 days. So every 50 days, you're going to have a major zone or region level issue with the DNS, with something or the other, right? And so making the database resilient is super important. And if it's not built in, a lot of teams keep working to make the database resilient. And when you put into context, on one side, failures are increasing. And on the other side, your number of applications is increasing, which means you have more databases. This becomes a difficult problem. So built-in resilience is super important, and it benefits organizations because you can focus on what matters rather than focusing on how to make the database resilient, which is not really the core goal of a business, right? So hopefully that answers your question, Bruno. Okay, so let me go to, let me keep going here. All right, and we'll circle back for a couple other questions. Okay, so the thing that we've done most recently in YugabyteDB is that we have made sure that the Postgres optimizer, this cost-based optimizer, works exactly the way it does when the data is local, just like it does in Postgres, and transparently, like takes into account distributed execution when your data set grows bigger. So it does things like moving code closer to data rather than moving data closer to code. And then we enhance specific queries to even get better performance than Postgres, because now you can use many nodes. And there's a lot of optimizations at the storage layer. But net, it is transparent, right? Like you can simply start with single node and go distributed. So this is the way to visualize it. Single node Postgres is local execution built for low latency and doesn't really care about remote distributed execution. And YugabyteDB, until recently, used to be primarily focused on distributed execution, which was scale and resilience. And you may or may not get local latency. You can if you focus on writing the query in a scale-friendly manner, but you won't if you already have an application, because it didn't focus on local execution. However, with the latest release, we actually have imbibed both. It can do local execution for low latency with resilience, and distributed execution for at scale performance and resilience. So you're able to get the best of both worlds in a transparent manner, right? And just to get a little bit into how this works under the hood, you start with some schema, right? And let's say there's one table that's growing big, but it's not too big yet. You can move the entire database to a replicated system where all of your data is in a single co-located database. So there's one shard which has all of the data, all of the tables, right? And what that ensures is that your data is replicated and you have the availability and built-in resilience. However, your transactions are processed on this tablet leader alone, where all of the data is local. So whether you do a join or a transaction, it's still going to be high performance and similar to Postgres. And you still get your benefits of geographic replication of data. It's a log structured file system, so it gives you low latencies. It does really well in the cloud, et cetera, et cetera. And when the time comes, you can take your fast growing table and you can split it into multiple tablets and distribute it across the cluster and get your scale. So you can dynamically adjust scale and which tables need to scale versus which tables need low latency and don't need scale. And this is done in a more or less transparent manner. So So, that's really the thing that we added, which, we're very excited about. Hope you are too. So in net effect, what you find is you may start out with 200 small tables, all of them co-located. After a while, it may become 195 small tables and 5 large tables. And maybe a couple of years later, it is 190 small tables and 10 large tables, and the whole thing can move dynamically, right, at any point. And it supports all of the Postgres features, so it's the same Postgres. You don't need to rewrite anything or re-architect anything. Okay, so that's point number 1. And there are a couple of other questions that I'd like to take on right now. The first one is, how does YugabyteDB handle the different PostgreSQL isolation levels? Well, with YugabyteDB, we have kept it not just code compatible and like ability to lift and shift, but also the way it works, the way it functions, the way it does retries or error handling or gives you error codes. It's all Postgres compatible. So YugabyteDB actually does have the same set of isolation levels that Postgres has. So it does serializable, repeatable read, and read committed, all the 3 isolation levels with a pessimistic locking or wait for concurrency control inside. So in other words, that's a lot of words. What it really means is that it works exactly the same as Postgres. Okay, now the next thing we're going to talk about is the connection management issue, right? Connection management is a major pain in Postgres. And a lot of people complain about the fact that it takes a long time to establish a new connection, or the number of connections per node is, Postgres spawns 1 process per connection, and this causes a lot of pain point, right, in terms of how Postgres connections are handled. Now, how do we make this a strength? Well, let's take a look. Well, there are a bunch of other limitations, like connection management happens to be one of them, but there's a bunch of other limitations around vacuuming or, transaction ID wraparound, or, those of you that know Postgres know what I'm talking about. A lot of this are things we can fix with a new architecture, right? So with YugabyteDB, we've taken explicit care to make sure we fix all of these issues. And a number of others are actually, they come with cloud native architectures. But, let's keep going. So with the connection management, I'm going to skip this. This is mostly about how replication and availability is handled in Postgres and Oracle. But we can come back to this to see how we do this with distributed architectures. Okay, so in a cloud native world, you need to do all kinds of scaling and availability, and that includes connections. How do you scale connections? How do you make sure connections are available? And the same thing for data and the same thing for queries, right? So, okay, so here's the way we have transformed the application architecture. So let's take a look at that and then come down to what we do specifically for connection management. This is a very traditional application architecture with Postgres. You have a bunch of different applications. They talk to a load balancer. The load balancer talks to a connection pool, and the connection pool talks to Postgres, right? And the issue with this type of an approach is that you need to maintain the number of logical connections in the application. You need the load balancer to be aware of how many physical connection pools there are. The connection pool itself is another external piece of software you have to run and make sure it's always available and monitor it and manage it and scale it and set up authentication with the database. All of these are pain points. And finally, you need to carefully maintain the number of physical connections and protect the database. Otherwise, Postgres would fall over, right? And this is why people have pain with connections. Now, another issue with an external connection management is, it doesn't do pass-through authentication. Like, you have to set it up. Like, if you're doing LDAP, there's really no way to use an external connection management like a connection pooler. And you have to set up your connection pooler in different modes, like, session mode or transaction mode or statement pooling mode. And oftentimes you don't know what your application does. No one knows because people are using various frameworks, and it's whatever the framework does. A new version of the framework may choose to do a completely different thing, which breaks connection pooling. So here's the changes we did. So the first change is we replaced YugabyteDB with Postgres with YugabyteDB here, which is a horizontally scalable database. So your physical connections that were hitting one node on Postgres can actually now hit multiple nodes. And so you don't really have too much of a scale pain point on the database side. But that's not all. The next question we asked ourselves is, why should anybody use an external connection pooler when we are a scalable database that's high performance? So we took the connection pooling software and built it into the database and built a whole bunch of other goodies in there, such as availability comes for free with the database. Similarly, authentication and authorization is done by the database as a pass-through rather than the connection pooler doing it. And we can do that because it's now a part of the database as opposed to an external system. So that means you move all of the connection management stuff into the database, and you have all of these physical connections and logical connections that the database deals with, and you don't really need anything else on the ingress side, right? And lastly, we said, load balancer, do you really need it? Well, in some cases, there's a perfectly valid reason to have load balancers, but we could get rid of it because the database cluster is aware. If you connect to one node, you can discover the topology of the entire cluster in YugabyteDB. So that's what we did. We made a new version, a new library for the JDBC driver. We call it the Smart driver. And any of the Postgres drivers, they're library compatible. So you just link your executable against a new library, and it's going to connect to one node, discover all the nodes in the cluster, and start doing a round robin transparently, right? So that means that you are able to simplify your application architecture tremendously with YugabyteDB, right? And this is in a large part made possible not only by the Smart driver, but more importantly, the connection manager that we introduced inside YugabyteDB, which is a connection pooler with built-in authentication and a whole bunch of other stuff. So here's what we're able to do. So, and the other good portion with the built-in connection manager is you don't have to set it up in any mode, like a session mode or something else, because it automatically understands, for example, various features such as session variables. It knows how to recreate session variables when it routes across sessions, or it understands temp tables and sticky or pinned sessions. It understands all of these things and figures out and does the right thing because it is a part of the database and it has access to taking a look at what that particular session is doing and do the right thing. So here's something that we were able to do. If you take Postgres and run a number of connections, right, like in parallel, so you're trying to establish a lot of parallel connections because that's what happens in the real world. Right from 250 connections all the way to 6,000, you notice that PostgreSQL takes much longer, this is the gray bar, than YugabyteDB to establish all of those connections. And the more the thundering herd of connections that come in, the faster YugabyteDB gets because of this change, right? And all of this is transparent to you. It just looks like a database. And all of these tests are on 16 vCPU to 16 vCPU machines, so it's like for like comparison. Okay, it's not just faster connections, it's about 5 times more connections as well. So if you look at if you keep increasing the number of connections on YugabyteDB, this is the orange line, which is how do connections go up? How long does it take and how quickly does it go up? And the gray line is how long it takes and how much does Postgres go to, right? And as you can see, with YugabyteDB, you can get over 25,000 connections, but with Postgres, you're in the 5,000 to 6,000 range. And lastly, as you introduce new workloads and as the total number of connections on the database keep going up, an existing workload has the same throughput. So irrespective of the total number of connections in the database, any one workload has the same throughput. Obviously, if you're running it with too many connections on a particular machine, your latencies would go up. But for those spiky situations, when a lot of new applications come up and try to establish connections, you can survive those spikes and ride them out with just higher latency, which is incredibly better than the database actually taking a downtime or the throughput going down dramatically across the board. So that was the second point about pain-free connection management. Let me see if there are any questions. There is a question on how does the new cost-based optimizer compare with the PostgreSQL optimizer? So maybe let me just give a couple of, maybe let me just give a quick answer to that. We reuse Postgres code, which means we have full access to everything that Postgres does. The new cost-based optimizer in YugabyteDB makes sure that the table statistics and the way queries are composed look exactly the same as Postgres when the data is local. And as the data starts getting distributed and remote, it changes the execution plan to match, to take network into account, right? So if it's local, it's going to have increasing parity with the Postgres optimizer. But when you start going into multi-node and multi-region deployments, it'll start understanding things like, you might have a situation where you have a index in a multi-region deployment. Your regular Postgres may opt for a query plan where you look up the index and then you look up the primary table because it's much quicker. But in a multi-region deployment, looking up the index and then looking up the primary table may incur too many RPCs, making your effective query very slow. And in some scenarios, it may just be better to full scan the primary table because it's much quicker. So these type of things transparently are taken into account. But if your data is not multi-region in a single node, it just works like Postgres. So I would say it transparently extends the Postgres optimizer. Okay, other questions? So if you guys have questions, yeah, feel free to keep dropping them in the Q&A box, and we'll continue to answer. But let's go to the third section, which is on easy active-active deployments. Okay, so what are we really talking about here? If you take a traditional database, Oracle or even Postgres, like Oracle is the gold standard that a lot of folks are used to, and Postgres is trying to go the direction of Oracle to emulate what it does. But this is roughly what happens. If you're inside one region in the cloud and you want active-active replication, you typically have two instances, a primary and a replica or a standby. And you have asynchronous replication. And sometimes, it lags the replica. And sometimes you wait to write the replica before acknowledging, so which means that they're both in sync, right? If they're in sync, you get into availability issues, but we will ignore the availability issues for now of the writes. Your latencies can increase quite a bit, but we'll ignore that for now. The real issue is you're going to the cloud, which is multi-zone, and you have these two zones with these two databases, but what happens on a failure? Somebody typically has to come and say, look, my primary is down. I'm going to promote the standby or the replica to the new primary, which is a manual operation and which can never be done really quickly, right? You can never do it quickly enough as a human, right? So how do you automate the failover on a node or a zone outage? Well, the typical approach is to use an observer node, right? And the observer node keeps looking at the primary and the standby, and it says, okay, primary is down, let's promote the standby. But the problem is, where do you put the observer node? If you put the observer node in zone A, and if zone A goes down, there is no observer. The same thing if you put it in zone B and zone B goes down. So typically, folks put the observer node in zone C, a different zone. So you have an observer with a primary and a standby. Seems to be okay, right? But the problem here is that if zone C goes down, you need to figure out who would bring up the observer. In other words, who would observe the observer, right? That's a problem. And it's also an asymmetric setup, which means it is harder to operate. Like the failure of the different components have different runbooks. Like you have to know, what does it mean if zone C goes down versus A versus B? What do you need to do, right? And there's other issues. Like, for example, any failure here requires a full rebuild of all data. So if you have like a terabyte of data on the primary and the replica, well, that means that if any failure happens, like even like a 10-second network partition, you have to rebuild that entire set from one of the sides because you don't know if they've gone out of sync or where you are, or et cetera, et cetera. Okay. And lastly, it's very difficult to extend the system to survive two failures, like one zone and one node. Like, how do you do that? Like, you need a replication factor 5, which makes it much more harder. You'll need more zones. It just gets more complicated to operationally make it work at the setup. So the last piece is that your application now needs to know at any point which node is your primary and which node is your replica. And you can do consistent reads and writes from the primary, and the standby or replica, you can perform stale reads. But this requires architecture on the part of the application. It needs to understand how to accommodate this. Like, you'll send all your stale reads to one endpoint. You now need to know, what is that endpoint? When has it flipped? All of these details, right? Now, with YugabyteDB, here's the change in architecture, right? All the three nodes are the same. It uses a consensus protocol to elect a leader at any point and automatically detect failures. So there's no notion of an observer. every node is an observer and every node is the database at the same time. So that means you've done away with a lot of the complex setup. If a zone or a node goes down, well, the others are watching for it, and the others will go ahead and elect a new leader and do the right thing. And it's very easy to extend this to a replication 5 setup because it's built into the Raft consensus protocol. Now, lastly, with respect to the application complexity, you can now perform reads and writes from anywhere, and it's going to figure out where the source of truth is. So you don't have to segment your application into everything that goes to the primary goes on this side, and oh, my replica is sitting idle, so let me send some stale reads to the other side. You can just use all the nodes in an equivalent manner. All right, so this is effectively the change or the transformation. It goes from like a primary standby or replica observer model to a, like it's just isometric. It's the same node everywhere. It's symmetric, and you can just have as many, and it uses a consensus protocol in order to replicate data and detect failures and elect new leaders. Okay, so that simplification makes it much easier to deploy the database without much operational burden, and hence, make your applications cloud native and therefore transform your databases to become cloud native as well. All right, so we looked at 3 of these things. Let's look at the next one, which is migrations, right? So, nobody loves migrations. We're still looking for the person that does. If you do join us. We have a lot of migrations in progress. However, the point is nobody wants to do migrations, right? And how do you migrate? So, I mean, thousands maybe, depending on where you are in your journey, but this is what people are trying to do. There's more and more microservices coming up. Every microservice is backed with its own database. And it's not uncommon now to rack up thousands of databases in your portfolio to back up the thousands of microservices that you have. So how do you migrate thousands of these microservices to a database like YugabyteDB when it's currently running on a traditional database like with the architecture we looked at in the previous section, right? So that's really the challenge here. Now, one of our completely open source products that helps you do this is to go ahead and migrate from, it's called Voyager. It's a completely open source product that will help you evaluate how easy or difficult it is to go from your source set of databases. So as we can assess your portfolio of databases, you can identify the level of complexity of each migration. And there's a set of workflows to help you, migrate to the new database. Now, there's a lot of community asks here. The target for Voyager so far is a YugabyteDB cluster, right? Because it is a cloud-native migration utility. But there have been a lot of asks to see if we can extend this to make it work for vanilla Postgres as well. So if you're folks that have such asks, do reach out to us, like, our community Slack, or, you can drop in a comment here or a question here, and, happy to discuss with you folks offline. But this is right now primarily about taking databases like Oracle or SQL Server or DB2 or one of these and doing a migration over to YugabyteDB. So firstly, you assess your portfolio, you figure out which databases are easy as shown in the diagram there, and you can go ahead and get started with the easy ones and defer the harder ones to a later point. So this is really the second thing that we have or we've announced is it's not just the ability to assess and convert your schema, it's also the ability to do live migration or replication of updates. So your initial state, as shown on the left, is an application running on Oracle. Your final state is you want your application to run on YugabyteDB, 3 of them, in a cloud-native manner. And in the middle, what we do, the way you get there, is by deploying Voyager to do a live migration from Oracle to YugabyteDB. When your app is still running on Oracle, all your updates are forwarded transparently to YugabyteDB, and you can do your, once you've caught up, you can do a cutover of the live application from Oracle to YugabyteDB, and you can reverse the direction of the updates and keep your Oracle as a standby while you run it on the YugabyteDB cluster in a cloud-native manner. Right? So if you're interested, do check it out. It's completely open source. But anyway, these are the 4 steps. You prepare your source clusters and do an analysis and planning, etc. And then you migrate schema, migrate data, and cut over, right? Like these are the 4 steps you follow. Live migration is obviously referring to the migrate data. and then there's a cutover. There's actually a fifth step you can do where you can set up a like a failback environment, right? Like where you can make sure if there's an issue, you can go back to your old stack while you fix it. Okay, so that was on migrations. Let's see if we have any questions. Okay, so there's a question here, which is what source databases are supported by Voyager? Currently, Voyager supports Postgres itself, MySQL, and Oracle. So those are the three source databases. On the destination side, it supports YugabyteDB. Obviously, YugabyteDB itself is completely Postgres compatible. And that's what I mentioned. There's an ask for us not only to support YugabyteDB as a target, but also Postgres as a target. And so we're getting a few of those asks. So do reach out if you guys are interested. But anyways, right now we support Oracle, Postgres, MySQL. And we have asks currently on the roadmap for SQL Server and DB2, right? And it's completely open source, so would love even contributions or of any kind, right? Using it, feedback, code, anything is all of it is welcome. Okay, so let's keep going. The next section is on simple scalability when needed. So the trick is, you don't want to get hit by scale needs without being prepared for it, because it takes a long time if you have to change your application. So the trick is to not have to scale by changing the application. That's really the only way to scale, right? Scale quickly. And so YugabyteDB is horizontally scalable by design. And the way it achieves it is, you take a user table as shown in the diagram here on the right, and YugabyteDB will automatically shard it and split it into small chunks of the table. Each chunk is called a tablet, right? And this is done automatically, transparently, and it can be done dynamically on the fly as well, right? So essentially the way to think about it is each tablet contains a group of rows, fully transparent to the user, and you can control it, right? For more advanced, access patterns, or for very large data sets, you want that control. Now, once your rows are split into these tablets, which is group of rows, all the tablets together will give you back the whole table, and every row is owned by exactly one tablet. So once you've done that, then scaling is really about, you have a bunch of these tablets. When you add nodes, move these tablets to new nodes, and every node that owns a tablet owns a group of rows and is responsible for that group of rows, right? Replicating it, making sure it's updated, making sure it's ACID compliant, so on and so forth. So this is how YugabyteDB actually scales. In the real world, there are a lot more tablets than what you see here. So you would have 50, 100 tablets per node or more. And what this means is when a node dies, all of its tablets scatter over to many other nodes. So the impact of a node going out is actually reduced, right? And your availability is much higher, as well as your scale, because you add a few nodes, the tablets start moving one at a time. Each tablet takes seconds to a few minutes to move, and immediately your new node is active and starting to relieve your cluster, and you're able to scale very, very quickly, right? The most important thing about scalability is that to realize is that it's unpredictable. We've talked to many users and customers who have tried to predict, look, year one, applications 1 through 8. Let's take this example of a customer, hypothetical customer, and they predict applications 1 and 2 are going to see quite a bit of increase in usage, as shown on this slide, right? So they predict for apps 1 and 2 to scale, right? And when year 2 comes around, well, it completely is different. The year 2 plan is nothing compared to the reality, right? And I can actually give you a couple of anecdotes of this really happening, right? So before 2020, before COVID came around, any number of verticals, like the shopping verticals were focused, a lot of our shopping customers were focused on omni-channel experience, which is, you go into a store and they wanted to do crowd sentiment analysis to see which areas of the store get a lot of traffic, what are the items people are likely to buy in groups, and put it together, right? And then COVID hit and, no one went to the stores. It all became, let's pick it up curbside. So the feature changed from build, omni-channel or sentiment analysis all the way to, pick up curbside by ordering from home. So it became a flavor of e-commerce which blends in person and online, and that became the most important. Or delivery at home, make that happen, or telling you where the person delivering it is, or everything changed overnight. And COVID was a forcing function, but in general, our technological improvements year over year actually force applications to change in different ways than what is predicted at any point of time. So this is the reality, and the spikes are actually much higher than expected. And so scalability becomes a necessity, and it has to be transparent, right? Like, so for example, once again, if you look at the retail vertical, the shopping e-commerce vertical, the Black Friday, Cyber Monday, and these holiday seasons are much higher in traffic compared to most of the other times, right? And it's the same in every vertical. There are times when there's peaks, and the rest of the time it's much lower. So if you had a database that can scale on demand without impacting your application, you can actually scale for these peak events, and you can scale back down when it's done, or you can scale when your application grows unpredictably, right? And the unpredictable growth is often what is the precursor to success of an application in the cloud native world, which means that's the reason why everyone's building these apps and features, so that it just grows unpredictably, and we don't want to be beaten by the scale, by the very success that we've worked to achieve, right? So it's important to recognize that scaling transparently is the most important thing with zero downtime. Everyone talks a lot about horizontal or vertical. Horizontal scale can be achieved quickly. Vertical scale takes a little more time because you have to move your data, change your machine types, and so on. But whatever it is, it has to be operationally simple and with no downtime, right? That's the most important thing. And the way YugabyteDB achieves that is through rolling upgrades, where you go to one node at a time in the cluster and upgrade each one and scale. Like you can vertically scale each one, or you simply add a few more nodes and horizontally scale it as shown in this section. So you have both options. It's transparent to you. The application will simply continue to deliver more throughput, right? Without any application changes in a relatively short period of time. Okay, let me see if there are questions. No questions. Once again, feel free to ask questions, folks. This brings us to the last section, which is that of global applications. Right? There are like three reasons primarily why people think about global architectures, right? But before I go into those reasons, I think the most important change that we've seen, right, like in the last 10 years or so, is that the public cloud is here to stay, and people are combining private cloud, their own data centers, with public cloud regions, and people are present in multiple different public clouds. So that means that there are over 200 or 300 different geographic locations where you can actually have your data, right? And this gives rise to a number of different use cases for global applications, right? The first use case is you want your disaster recovery or high availability. You don't want the complete outage of a region to affect your application. So you want your data and your application and your database to be able to run in a different application as well. In a different region as well at the same time, right? So run it in multiple regions. The second use case is you have a global set of users and you want them to have low latency. So I want to do my, stock transaction, or I want to buy and sell using an e-commerce application. And I may be some users are in Europe, some users are in Asia, some users are in the US. They all need to have low latency, right? So that means your data needs to move closer to the users. And the third very important use case is around residency and data compliance. Now, GDPR laws require all of the personal data of European residents to live in European data centers. And the US data you might want to keep in the US, and the Asia data you might want to keep in the Asia. And a lot of countries, for geopolitical reasons, are starting to mandate keeping the data of their citizens or their residents locally in those geographies, right? So that means far-reaching global architectures are not so far-reaching and not so future-facing. They are here and now, right? And they're happening now. So let's take a look. Right? Like, so if you're going global, it's not just about a lot of data, it's about data distributed in a lot of locations, right? So if you're doing that, you need a number of different design patterns, right, to be able to do that. with a distributed SQL database like YugabyteDB, because replication is built into the database, we can actually offer a lot of deployment patterns, right? So here's an example of 8 different deployment patterns that you can do with YugabyteDB. I'm not going to go into what these design patterns are, because that's a whole another talk in itself about how you select them and how you architect your application and so on. However, it's important to call out that only 3 of these design patterns are actually used today when you're using a traditional relational database like Postgres. So you do active single master, which means you put a Postgres, like we looked at in a prior slide, in one region, and you put another Postgres in another region, you replicate in one direction, and you just read and write transactionally from on one side, and you may do stale reads on the other side, and you will flip over you promote the replica to the primary, and the primary you will demote it to a replica, and that's what you have in active single master. Active multi-master is you will write on both sides, but you don't get transactional guarantees, right? And read replicas is when you have a database and a bunch of other read followers, right? Like replicas that are read replicas, and you can just read from them. Now, there are a number of other patterns, such as giving you global transactional consistency, or getting your data resident to different locations, whether for latency or for data compliance purposes, or so on and so forth, that you can achieve with a truly distributed database, right? So these are some of the things you can achieve with YugabyteDB. Specifically, these other 4 are actually quite common. So a global database, for example, gives you global transactional consistency, but increases your read and write latency. The duplicate index pattern actually lets you decrease your read latency, so very low read latency from all regions with consistent data, so no stale data. However, it increases the write latency, right, at the expense of write. So you may have applications which require you which are okay with taking much longer for writes, but you absolutely want low latency but consistent reads, and so on and so forth, right? And these are patterns that you may want to mix and match, right? And so mixing and matching is like one microservice may want to do one thing and another microservice may want to do another thing. And this is traditionally very hard if you have to engineer your way around each of these solutions. But if the database gives you building blocks, that makes things much, much easier. Okay, so this is a part of a demo. If you're interested, do reach out. We have a full-blown demo of where you can take a look at how, and the demo does something. It takes a trading application and it simulates a user running in the West Coast and the East Coast of US simultaneously, and both of them have low latencies. And we take down an entire region in the East Coast and show how this thing continues to work. And the West Coast user experience is nothing, and the East Coast users' reads are still low latency, but writes increase in latency a little bit, right? So, and this is just the starting point. You can engineer it a lot better because these are like Lego building blocks that you can compose and comprise and get to do exactly what you want to do with it. Okay, so that was our making PostgreSQL even better checklist. So we looked at 6 things. We started out with keeping all the operations the same, everything in Postgres the same. Don't take away anything from it, store procedures, triggers, blah, blah, whatever it is. Keep it the same, or make it work like Postgres. But improve connection management, and in general, your application architecture can get simplified. And then, how do you get multi-region synchronous deployments? So for 0 data loss, very quick failover, high availability. You don't have to engineer anything. It's automatically taken care of by software. Migration, we talked about how to assess your workloads, move your migrations, etc. with Voyager as a completely open source product, and scalability on demand, but with no impact to the application. Most importantly, we looked at horizontal and vertical scale and how horizontal is quicker, but even with vertical, you need no impact on your application. It has to be operationally simple. And last but not least, global architectures and what are various things you can do with distributed databases. Right? So that brings us to the end of the list. But if you have other things in making Postgres better, do reach out to us. We'd love to hear what it is you're looking for. We are working on a number of other things. But anyway, YugabyteDB, it is PostgreSQL with built-in resilience, seamless scalability, and a lot more, right? And it's architected as a distributed SQL database. And our main goal is to eliminate limitations in Postgres, like to make it more broadly applicable while simplifying application architecture And it's whether you're modernizing your existing database or building a new service, our aim is to make it simpler. Right? So here are some real-world databases. Anecdotally, thought it might be interesting. We talked a lot about e-commerce examples or banking examples or whatever it is. So most of the North American retailers, if you're shopping online other than Amazon.com, you're probably hitting a YugabyteDB database to do your one thing or the other, right? Like either it's post-purchase or it's during purchase or your shopping cart, something or the other. Similarly, your smart cars, like a variety of different GM cars, like OnStar vehicles, all of them, the smart vehicle platform is the database backing it is YugabyteDB. Again, insane scale on that one. If you have a Comcast router, or like an Xfinity or Comcast router, you're hitting a YugabyteDB database behind the scenes. Same thing with a number of online banking services through a number of different companies. Like if you're watching Champions League or Big Brother or a number of other shows on Paramount Plus, you're hitting again YugabyteDB and so on and so forth. There are a lot of other things. So this is these are all use cases that require some level of transactional guarantees with scale and availability. You don't want these things to go down, right? And there's a lot more out there that that have similar properties. So that brings us to the end of the presentation. Once again, would love to take questions. I'll wait a second for questions. Once again, we are a 100% open source database. It's not just a migration product. The database itself is 100% open source. If you have questions for us, do join our community Slack, as it shows there, yugabyte.com/Slack. Check out our GitHub page, and we'd love a star. But we'd love to hear from you. So yeah. So let me pause here to see if there are more questions.
Awesome. Well, thank you so much, Karthik. It looks like that is all the time we have for today. But for the attendees, if you do have any last-minute questions or questions that you think of, please make sure to type them into the Q&A box, and we'll make sure to get them over to Karthik to get them answered for you. So thank you so much again, Karthik, for that wonderful presentation. Thank you again to the attendees for attending today's webcast. And of course, a special thank you to YugabyteDB for sponsoring today's event presented by 82mag.com. We hope you have a wonderful rest of your day, everyone.
Thanks, Victoria, for having me, and thank you, everybody, for listening. Thanks a lot.
Absolutely.